Okay, so we're going to record this meeting to the Zoom cloud. I will bring it down afterwards and actually have it on our YouTube channel. And everyone that attends this meeting, and even if you didn't, I'll send you the link in a few days once I get it set up. Good evening, everybody. My name is Scott Lytle. I'm the chapter chairperson here for the Southeastern Michigan IEEE EMC Society, and I welcome you all this evening. We did invite 6 or 7 different chapters around the country. So if you're in other areas, I'd like to welcome to our chapter. I see we currently have 39 out of 47 that signed up. So this is really great, as Karen was saying, because it's about standards. And who knew people would get so excited about standards, but that's a good thing. If you stick around for the whole meeting, after the meeting, we are going to have a drawing for 3 different Amazon gift cards, a 25, a 50, and a 75, but you must be present to win. So we use a random number generator and we go through the roster. And if you're still here, you'll be getting one of the 3 Amazon gift cards. Before we start this evening, I'd like to announce EMC Fest 2024. EMC Fest will be held in Michigan at the Livonia Embassy Suites. And again, that's May the 16th. We have 2 speakers, Doug Smith and Ken Wyatt. So for more information on that, you can go to www.emcfest.org. And you can sign up there and get all the information. 2 days prior, there's a Chicago mini symposium, the same speakers. That's on May the 14th. And there's a link actually on our website back to the Chicago site. So you don't have to write down anything. You can get to both of those on emcfest.org. Our next month is EMC Fest, but the following month, our speaker is going to be Keith Frazier. Keith is a local here. He works at Ford Motor Company. And on June the 20th, he'll be talking about EMI on electric vehicle radio. So that should be a good one. And before we begin tonight, dear Karen, on behalf of the IEEE Southeastern Michigan EMC Society Chapter 8, I wish to express appreciation for your presentation to our chapter entitled Overview of EMC Standards. The chapter has recognized your professional commitment to the education of our members with a speaker award, which includes a donation in your name to the IEEE EMC Society President's Memorial Scholarship Fund. Your name, topic, presentation, and donation may be viewed at the chapter speaker list on our website, along with a complete list of speaker awards going back to 2012. And I'm going to be emailing you a copy of this letter, Karen. Here. So this evening's speaker, again, is Karen Burnham. And coming through my papers here. Okay, Karen is the head. Oops, hold on a second.
Am I?
Hold on, okay. Okay, Karen Burnham is a principal scientist at Electro Magnetic Applications, or EMA, in Denver, Colorado. She's a iNARTE certified EMC engineer with experience in both the aerospace and defense, as well as automotive industries. At NASA JSC, she worked on the Orion spacecraft and pyrotechnic systems. She was able to work on the Dream Chaser spacecraft and the F-35 fighter jet. She spent several years working at Ford Motor Company on traditional vehicles like the Ford Edge and Lincoln Continental, and also on their newest line of electric hybrid vehicles such as the Ford Explorer and Lincoln Aviator. She sits on several international standards committees and was recently elected to the IEEE EMC Society Board of Directors. Over to you, Karen.
Hey, great. Thanks very much. Let's see. While I'm pulling my slides up, I think the one thing I probably should have updated my bio with is that I'm currently Vice President of Standards for the EMC Society, which has been a fantastic opportunity. giving me even more opportunities to geek out about standards. And given the audience that we've got tonight, thank you all so much for joining us and tuning in, and being willing to sacrifice a weeknight to a talk that's entitled Standards Overview, which I was so worried was going to be just incredibly boring. And honestly, my very first thought when I was invited to do this was, how can I make this not be boring? For a conference that EMA put on earlier this year, I was teaching at one of the workshops, and one of my slots I just did EMC basics, and one of them I wanted to do an overview of standards, and it just ended up being walls of bullet points with no pictures, and I was like, this just makes me sad. And so I did something kind of completely different because I had an in-person audience. But I know, because not everybody wakes up in the morning and is like, man, standards, except EMC people, might honestly be more likely to do that than your average electrical engineer or physicist or man on the street, as it were. But, in my goal of trying to make this less boring, it's like, what can I do to liven this up a little bit so it's not just wall-to-wall text? And I was like, competition, let's do some competition, head-to-head standards. But really, it's not about competition, is it? It's more about comparisons. And so it's probably going to be less WWE and more like Coke versus Pepsi. It's just, they're different, but they're both good. It's fine, whatever you like. But with that, I wanted to start with the category of radiated emissions. And, I wanted to kind of put some of these standards side by side. And one of the ways that I really got into standards in a much more in-depth way was when I moved from aerospace, where I started at Johnson Space Center, into automotive, where I was at Ford, and then back again, of course, as a consultant. Now I, sort of jump wherever I need to go. But knowing that we're all looking at the same physics, electrical engineering fundamentally doesn't change, but there's still so much difference from one standard to another. And so one of the things that I really wanted to do with this talk tonight was, because I know, again, I'm talking to an audience of EMC engineers, an audience of EMC engineers who are willing to call into a webinar on standards. So you guys know some standards, right? But I wanted to sort of bring together some options that you don't usually see put side by side. And especially with the goal of thinking, not only, can I compare these standards head to head, but what's out there? If I'm having trouble with a particular test method or a particular unit, and I need to start thinking a little laterally, I've obviously when you are testing for record, you follow the standard to a T. But there are times when, maybe that exact standard isn't necessarily the exact right thing for the thing that you want to know, the thing you want to learn. And so what I'm hoping is that, by kind of doing this overview, I'll give folks some inspiration of other places to look than sort of the standards, if you'll pardon the expression. And I just saw lightning outside. So if, speaking of electromagnetic environmental effects, if I lose power, you'll know why. But I thought I'd start with some that are, again, very, pretty much everybody kind of knows these, at least to some extent. This is all dealing with component radiated emissions. We've got CISPR 25, which is really focused on the automotive industry, MIL-STD-461 RE102, which is mostly focused on aerospace and defense, and then FCC, which the FCC doesn't specify its own test method. It points to ANSI C63.4 for its test method. So, we're talking FCC, we're also talking ANSI, but that's really, aimed at consumer electronics. So one question that does come up is, if I have some electronic component, device, what have you, something that would normally be tested to one of these limits, if I have its test data for one of these standards, can I say anything intelligent about how it might perform when tested to the other standards? So, as you're looking at these limit charts, there's a few things that we can note. So one thing is that at least they're all in the same units. That's one of the first things I check because I've been burned by that before. So everything here is in dB microvolts per meter. So that's a good start. They cover different frequency ranges and they're at different levels. But then you start digging kind of further into the details. And the first thing to really note is that the CISPR-25 and MIL-STD-461 test methods and limits are all written with the assumption that you are taking your data at 1 meter away from the unit under test. Whereas the FCC is looking at something 3 to 10 meters away from the unit under test. And that means that your CISPR and RE102 data sets are taken in the near field, almost certainly. I mean, certainly once you get up to some of the higher frequency ranges, you might be able to say you're in the far field at 1 meter. But for a large chunk of the frequency range that those tests are concerned about, you're in the near field. And that, that brings with it some complexity. Whereas in the FCC world, 3 to 10 meters, especially from 30 megahertz to 1 gigahertz, that puts you fairly safely in the far field. And so I would like to point out, I know a lot of you know Ken Javor, or you've seen some of the talks that he's given. I know he's talked to this chapter before. Ken Javor says, don't extrapolate 1 meter measurements to 3 or 10 or vice versa. He's got a great series of articles in Compliance over the last year or so, where he talks about near field versus far field and some of the measurement complexities that come in, especially when you're taking near field measurements. If you look at the FCC limits for 3 and 10 meters, it is a straight linear extrapolation. The 10 meter limit is lower by a linear factor than the 3 meter limit, which makes perfect sense. But you shouldn't go the other way. You shouldn't go from 3 meters to 1 meter, because at that point you're trying to extrapolate from the far field back into the near field, and that does not go well. So that's one thing, that one of the first things that we can say is you probably should not assume that just because something passed FCC limits at 3 meters, that you can say with any confidence that it would do well on an RE102 style test at 1 meter. So that near to far field measurement difference, that makes, has some significant impact. If we look in depth into the test setup a little bit more, aside from the distance between the unit under test and the antenna, there's a couple other things to notice here. And one is that RE102 and CISPR-25 both have the unit under test mounted on or very close to a metallic ground plane. So, you've got a table, it's got a certain surface area. That surface area is pretty much a consistent ground plane. It's usually all copper. And then, if you have a unit with a metal housing, which is very typical for aerospace and defense, and if in the real installation, that unit would be bolted to chassis, on whatever spacecraft, satellite, aircraft that's going to be installed on, then you would bolt it straight down to the conducted ground plane. Same thing for CISPR-25. Again, assuming most of these modules are eventually going to wind up in cars, most cars still are made of steel or some other conductive material. They have a conductive chassis. And so if you have a metallic housing and it will be bonded to chassis or mounted to chassis, you can mount it straight on the ground plane. If you've got, plastic housing, or, it's for whatever reason, it's never going to be that close to chassis, you just stand it up off the ground plane by a standard 5 centimeters. And so that, that very much represents the assumptions that go into writing the standard about how these units will ultimately be used. Now, the FCC and the ANSI test method, in contrast, everything in there is dielectric. You're standing up your test article either on a plastic or wood table with no ground plane on it. Again, that makes sense. The FCC is concerned with standalone consumer electronics or consumer devices, generally speaking. Cell phones, computers, hair dryers, that kind of thing that aren't going to be installed, or at least you certainly can't assume that they're going to be installed anywhere near metal. Most of the time they're being used in a residential or an industrial environment. And so they're going to be, far away from metal. So the test setup reflects that assumption about how the end item is used. But again, that's another difference between the FCC test method and MIL-STD-461 and CISPR 25. The existence of that ground plane makes a significant difference in the data that you're going to measure. So this kind of goes the other way, where I would tend to say, just because something was successful in, for instance, a CISPR 25 test, I wouldn't automatically assume that it would be successful at an FCC test, because you don't know, you can't necessarily make an assumption about how that ground plane affected things. So, you can really start to see the thought processes behind how these standards get put together, specifically for the industries and the applications that they are, most closely associated with. So looking now at conducted emissions. So again, sticking with MIL-STD-461 on one side, so CE102, and FCC on the other side. So FCC has a conducted emissions test that goes 150 kilohertz to 30 megahertz. And so again, check the units on both sides, at least it's all the same units, dB microvolts on both sides. But one of the first things that I notice is that, one of the first things I notice is different frequency ranges. So FCC is 150 kilohertz to 30 megahertz. MIL standard is 10 kilohertz to 10 megahertz. It's just a difference. And by the way, MIL standard does have a CE101 that is addressed to the even lower frequency ranges, but that really is focused on audio interference. So the kind of interference that like a pilot would end up hearing on a headset. So even lower than what the FCC worries about. So different frequency ranges. But then the other thing is that all the MIL standard measurements are taken with a peak detector, or your spectrum analyzer or EMI receiver set to peak detection. If you look at the FCC limits, they've got one limit for quasi-peak and one limit for average. And those are not necessarily intuitive. Well, average is very intuitive. Average is intuitive, peak is intuitive, quasi-peak is what on earth is quasi-peak? And again, how can you compare some of these different detection methods? Well, so one of the really nice tricks for FCC and some other tests that have quasi-peak limits, I think CISPR 12 might also, if I recall correctly, you can sweep through a test, sweep through your whole frequency range with your detector on peak, and it is accepted, and it's probably true like 95, 98% of the time, that as long as all your peak values are beneath your quasi-peak limit, then you can say that even if I went back and tested to quasi-peak, it would never be higher than the peak limits. So I do a really fast sweep on peak hold, or peak detection. Everything's below the quasi-peak limit, and I can wash my hands and say I'm done, which is good because the quasi-peak method requires significantly more dwell time in every frequency band. And so it's a much slower test to run. And then of course, average is averaging, right? You're sweeping through, again, it takes just a little bit longer, to average, over certain, a number of bandwidth slices. Again, but averaging is pretty intuitive. Now, I think folks in automotive are probably more attuned or used to quasi-peak than folks from other disciplines. But just for folks who haven't heard, or for whom this might be new, because if you go looking for what is quasi-peak and why is quasi-peak, it is hard to find information on that. So just to let folks know, the principle behind quasi-peak detection is that a single persistent tone is more annoying to a human listener or user than static-y background noise. And so quasi-peak will hold in a frequency range for a certain amount of time, and then it kind of weights the signals that it gets. And so if something is sustained at a particular frequency, that will show up as being more severe or higher than if you've got noise, but noise in any particular frequency bin isn't sustained over time. So that kind of hiss and crackle gets not, well, I guess you could say suppressed. It gets kind of less weight when you're doing quasi-peak measurement than a sustained tone. And, you know, when you're going back to the history of a lot of these things, you know, especially standards that have been around for a very long time, a lot of them were dedicated to protecting very old radios. AM radio, obviously we still spend a lot of time protecting AM radio for cars and automotive users. And Ken DeVore, I posted this on LinkedIn. He's got a really nice video that I think is specifically CE102 based, of the original World War II vintage radio that this test and CE101 was originally meant to protect. And that's a radio that's so old that it wasn't fed with coax. It was, you know, grounded to chassis and then had a single conductive wire coming out from it. So a lot more susceptible to this kind of noise than a modern, what we think of as modern electronics or modern radios would be. So, you know, diving into the history of these things can be more entertaining than it should be. So that's one of the first things that I noticed comparing these two. And then we get back to the testing setup once again. So MIL standard is assuming everything gets installed in some kind of metal chassis. So 5 centimeters to the ground plane. FCC is assuming that you're mostly using this out in free space. So, you know, 80 centimeters to the ground plane on the floor. And one of the things I should have mentioned before I moved on was that as we've been comparing back in radiated emissions, FCC versus MIL standard and CISPR, you know, while I wouldn't recommend taking something that's compliant to CISPR and assuming it's compliant to FCC or vice versa, if you've got something that that you've got test data based on a CISPR 25 test setup, and you wanted to say something about how it would perform on a MIL standard RE102 test, you can probably say, you know, make a fairly direct comparison from one to the other. They're both at 1 meter. They both have the same conductive ground plane test method. So, you know, those are much more closely related than, for instance, FCC. One of the other things that was interesting when I started digging into the comparison between C102 and FCC is how they treat their LISMs. And again, this goes back to the assumptions of where these units are getting their power. Now, you know, there's a whole history of LISMs and how they came to be developed, and I'm going to point back at Ken DeVore again. I've been reading a lot of his stuff lately, where he actually, you know, like dug down into interviews and found the name of the guy who invented the first LISM. He wasn't actually an EMC engineer, and it was back in the 50s. So that's another article you can look up on Incompliance or on Ken's website. Definitely a fun read. But if you look at the two impedance curves of the LISMs used for FCC and CU102, and then the schematics, you'll see that they are different. And you could have maybe predicted this a little bit from the limit curves as well, when you notice that CU102 has a base limit based on something that is getting 28 volt power, and then it kind of extrapolates up from that. And that's 28 volt DC power, because that is pretty much the standard power bus for aircraft and a lot of spacecraft as well. Whereas the FCC, when they're doing conducted emissions, they assume that you are plugged in to wall power, so that you're getting 60 hertz AC power. And to match the same impedance level. So to get to that, 50 microhenries or 50 ohms across the frequency range that you want, if you're dealing with AC power versus DC power, you need to have slightly different schematics. So in terms of comparing, one set of test numbers to another set of test numbers, does this difference in schematics make a difference? It's a little hard to say. I mean, ultimately, it should be presenting the same impedance to the measurement equipment, but it's just another one of those sort of subtle points to keep an eye on. Is that even the guts of the listen through which you are taking your measurement can be different. Now, so again, assuming DC power for MIL standard, assuming AC power for FCC. Now, while I am on the topic of conducted emissions, have you heard the good word? This is one of my evangelical kicks. Goddard Space Flight Center Standard 7000B, which is also known as GEVS. So that's the GEVS on the good book there. This is a standard I first tripped across as part of customer project just a few years ago. GEVS is an environmental verification standard, so it includes a lot of stuff other than just EMC. So it's got stuff on thermal and shock and vibe, and I think it might have salt fog in there. But section 2.5 is all EMC, and it is pretty much all written by Ken Javor and John McCloskey. And when it comes to doing some of the conducted emissions testing, for one thing, they have a common mode conducted emissions test that MIL-STD-461 does not have. I mean, in general, the Goddard Space Flight Center 7000B is a very highly tailored version of MIL-STD-461, specific for the kind of space missions that Goddard is most likely to sponsor. So these are unmanned missions. They are primarily science focused, and they're primarily small. Now, I say primarily small because John McCloskey spent a good chunk of his career working on James Webb Space Telescope, which is not small. But, a much more typical Goddard satellite would be 1.5 to 2 meters on a side. Right. So that, that influences a lot of choices. Again, almost all of them are made of metal or have a metallic chassis, so that drives those decisions. One of the things you can see here is that instead of using a 5 microhenry or a 50 microhenry listen, they actually go back to an older technique and use a 10 microfarad network of feed-through caps to do their line impedance stabilization. And especially with, because when you've got a satellite, you've basically got a battery that's providing all the power for the satellite, and then that battery is getting constantly recharged, usually by a solar array. That's the most typical test setup. And in a small satellite with a battery-driven power bus, the sense is that the 10 microfarad cap network is a more accurate representation of the installation than a 5 or a 50 microhenry listen. So again, it's having access to those kind of options and sort of digging into, we're so used to 50 microhenry listens, but is that always the right choice? Would a 5 microhenry listen sometimes be more appropriate? You could argue that for automotive vehicles that tend to be, no more than 3 or 4 meters long, 5 microhenry is sometimes the right call. For smaller, even smaller satellites, this is an alternative method. Now, another thing that I really appreciated about GEVS is it's structured in much the same way as MIL-STD-461. So there's a section that lists all the different tests and test methods and limits. And then there's another section that goes through the same, paragraph structure, but acts like the appendices of MIL-STD-461. So there's a wealth of additional information in there. And there's a very long section on the use of the CISPR 16 absorbing clamp in conducted emissions measurements, in particular for common mode and for particularly at higher frequencies, like in the tens of megahertz. And boy, after reading that, I was sold. I was like, I swear I will never, if I have any option, I will never test high frequency, common mode, conducted emissions with a clamp on current probe ever again. I'm using this every chance I get. Now, does that make the current probe, the clamp on current probe approach wrong? No, absolutely not. But there's some great explanations in GEVs of things to watch out for, pitfalls that certain test methods can fall into, advantages and disadvantages of different approaches or different test equipment. And there's the people who write standards, and of course this isn't true for every standard, but for some reason the military and aerospace community is particularly good about this. They just dump this wealth of information and guidance and years of experience and lessons learned into these appendix sections. And if you have the time and the leisure or the the urgent need to get more information on some of these different tests and test methods, man, take a look at all those resources. That's valuable information. And also coming from the MIL standard and aerospace world, that's all free. We have to pay for IEC 61000 or for ISO 11451. But I mean, I absolutely do not have everyspec.com bookmarked on all my browsers so that I can find NASA and military standards whenever I need them. No, I don't have that at all. But sites like everyspec.com give you free access to not just the most recent version of everything like MIL-STD-461G, but all the historical versions as well. So going all the way back to, from G to D to A. So if you have a question about, yeah, but where did this come from? Or what was it originally? You can find all that there. So again, this is just all in the spirit of when you have the opportunities to think laterally and sort of escape the bounds of one particular standard that you've been using, there's a wealth of options out there. Getting back to the more technical content, pardon me. Before I leave the subject of emissions measurements in general, so this is true for both conducted emissions and radiated emissions, take a look at the measurement bandwidths that are imposed from the different standards. So comparing MIL-STD-461 to ANSI C63.4. At the lower frequency ranges, MIL standard says 10 kilohertz and ANSI says 9 kilohertz. And then from 30 megahertz to 1 gigahertz, MIL standard says 100 and ANSI says 120. I don't know why. If anybody on the call knows why, then please at the end, when we're doing Q&A and conversation, please let me know. I'm like, why are they so close and yet not, right? Because that just makes it that little bit harder to directly compare one set of measurements to the other. Not impossible, obviously, but you're like, but why? So that's on my list of unanswered questions that maybe someday I'll find the right person and I'll get an answer. Another topic that I wanted to touch on was ESD. So in the most recent version of MIL-STD-461, there's now a CS118 test, which had been kind of a in demand. People have been asking for this for a long time. And I took a look at these two charts, or when I first got my hands on a copy of Rev G, I opened this up and I looked at the chart on the left and I said, gosh, that looks mighty familiar. And I pulled up IEC 61000-4-2. I was like, oh, okay, CS118 is just a cut and paste of IEC 61000-4-2. Okay, that makes sense. And then a colleague of mine, I mentioned that to a colleague of mine, he goes, oh yeah, well, except there's some subtle differences. I was like, okay, so I went back and checked and if you take these two charts and then you look up the tables that have all the percentages and IPs and dwell times and everything like that, these are, as far as I can tell, completely identical. These are the circuit schematics. I mean, obviously they are drawn very slightly differently. But fundamentally, it's still basically the same. You're discharging through 330 ohms. You've got a 150 picofarad in shunt. Your charging resistor is, is in the mega ohm range. This all looks pretty identical. And even the other thing that's specified by CS118 is the shape of the probe tips for the ESD simulators or ESD guns, both for air discharge and for contact discharge. And again, as far as I can tell, these are identical. It's like, 12 millimeters plus or minus 1 millimeter, a total length of 50 plus or minus 1, even the angle, 25 to 40 degrees for the pointy one. So as far as I can tell, CS118, IEC 61000, completely the same. Again, so if somebody knows about some subtlety that I'm missing, please let me know at the end. I'm hearing a siren outside now, and it's really pouring. So again, if I lose power, you'll know why. Or if you see me get sucked out a window, you'll know why. But the one thing that again, in the spirit of opening up options and thinking a little bit laterally, both MIl-STD-461 CS118, 61000-4-2, and all the other ESD standards that are derived from 61000-4-2, which is by far the most commonly used ESD test, they're all based on a human body model, right? They assume that somebody, on a cold winter day is shuffling across, a carpet or whatever have you, reaches for a particular thing and discharges, as they're coming close to the unit. The human body has a particular or a typical resistance, a typical capacitance, and that's reflected in these kind of schematics. But what about those times when you have a concern about ESD, but not from a human source? And the place I run into this is in spacecraft charging. So you've got a spacecraft, it's orbiting the Earth, it's going through a plasma environment in low Earth orbit, and an even more severe environment in geosynchronous orbit. And if the surface of the satellite and the solar rays is not conductive enough to let charge sort of bleed off or evenly distribute around the surface of the vehicle, it'll build up in certain spots and then discharge to whatever it happens to be near. And this is particularly a known problem on solar arrays. So if solar arrays don't have conductive coatings, then a lot of times charge will build up in a particular spot and then it'll zap through a particular solar cell, taking that solar cell offline. And if this happens repeatedly over time, it degrades the charging capability and the power capability of the satellite, and it shortens the satellite lifespan. The other time that you might see this is if there's a part of the satellite surface that for whatever reason didn't have a conductive surface or didn't have an adequately conductive surface. Maybe part of it got anodized for some reason. Charge can build up in that spot. And what you really don't want to have is to have that then zap to your payload. If you have sensitive measurement instruments on the outside of your spacecraft, you really don't want that to get zapped. Or if it is going to get zapped, if you know that's a risk, you want to be able to have some assurance that it will survive the threat. But that threat is completely different than a human body model, right? You are not discharging through 330 ohms and 150 picofarads. So I would like to introduce you to MIL Standard 1541A. I believe this standard is no longer, no longer active. Although I did not have a chance to go back and double check that. But I believe that it's not currently being updated. But it's one of the few places where you can find a recommended ESD test setup that is tailorable for discharges that are not based on a human body model. So if you have some information or some sense of what your actual resistances and capacitances should be, this is a way to do a test setup that is more flexible as it were, than the sort of traditional 61,000 ESD gun. So again, that's just in the spirit of looking at what's out there. Oh, one last one. So talking about filters. So I was in conversation with the customer, and they were building a big shield chamber. They were pretty new to the business. They'd picked out some power line filters, right? Because if you've got a shielded enclosure for whatever reason, you're going to need power on the inside, but you don't want either noise from the inside getting out or noise from the outside getting in. You want to maintain the shielding integrity of the whole chamber. And they had selected power line filters that were compliant to MIL standard 220. But the customer that they were working with wanted to do in situ measurements to make sure that when the power line filters were actually installed, that they were performing as advertised. So 100 dBs of attenuation from 14 kilohertz to 10 gigahertz. So I went down rabbit hole with MIL standard 220, because MIL standard 220 states very specifically, and it's an up-to-date standard, this standard covers a method of measuring in a 50 ohm system the insertion loss of feed-through suppression capacitors and of single and multiple circuit radio frequency filters at frequencies up to 10 gigahertz. And the only test setup diagram in MIL standard 220 is what you see in front of you. It has either a VNA or a spectrum analyzer with an RF output going to the device under test and an RF input. This standard assumes that, and it even says, it is for radio frequency filters where everything has a coaxial connection. Man, I'll tell you one thing, those power line filters, they are not coax and they are not RF filters, or at least not, in the sense that they were designed to filter, RF signal lines. These are designed to filter power lines. They don't have coaxial connections. And, it really, I went down a whole bunch of rabbit holes trying to find how, if you can't just plug in, coax on one side, coax on the other to go back to a VNA, how are people quote unquote certifying these filters to MIL standard 220? And I finally found a kind of blurry test picture that basically shows you've got the coax coming out, and then you just split the outer shield on one lead to the ground of the chassis ground of the filter, and then the center conductor of the coax goes to the power line input of the power line filter, and then vice versa on the other side. Is that 50 ohms all the way through? I don't know. I mean, maybe. But as I was doing literature searches, people were like, yeah, MIL standard 220 became the industry standard. It's not the right test method for what it's being used for, but it's the only thing out there. Or for a long time, it was the only thing out there. Which is one of those cases where a perfectly reasonable standard, MIL standard 220 is, a really good standard for testing testing RF coaxial filters. But it got misapplied early, and now it continues to be misapplied, if you'll pardon me saying so. I mean, I'm not in the power line filter business, so I don't mean to insult anybody, but it just seems so odd that this is the standard that was adopted. Now, there is an alternative now. This was identified as an issue, and there's an IEEE standard 1560. It came out in 2005, and it is specifically for testing the filtering capability of power line filters at RF frequencies. And basically this standard has about 8 different test methods that cover different frequency ranges, and that also cover, like, when you're proving out a prototype versus when you're just doing quality assurance. It's not a perfect standard. There's kind of a gap, I would say, of a really thorough test that's officially sanctioned to cover 500 gigahertz to 1 gigahertz, which I found a little strange. but it is exactly the right standard to evaluate these kind of power line filters. So I suspect that there's just an inertia where everything has been qualified to MIL standard 220. Obviously, it's good enough. I'm imagining there aren't a ton of user complaints. The filters are probably very well built, and so are no matter how they're tested, they're able to function in the precisely the manner that the customer needs them to function. And if you've been doing something for a long time and it's been working, why change it? Especially why change it when you'd have to potentially invest in new equipment or what have you. So there's standards, and then there's how you use standards. And some you kind of can't blame the standards writers for how things get used later on. But one interesting thing is that we're currently in the process of trying to renew IEEE 1560. So it is one of those standards. It's not necessarily the most used standard ever, but it is referenced in a lot of government contracting. And so we need to keep it active so that it can keep being used in that way. Government contracts aren't allowed to refer to obsolete or inactive standards. Some of you may have seen an email go out asking for feedback on 1560. We're starting to stand up a working group. We've kind of got two ways to go with it, depending on who joins the working group and how eager and dedicated everybody is. We can either just rubber stamp it the way it is and go through the IEEE Standards Association process for renewal, which for some reason has as much paperwork complexity as writing a completely brand new standard. We don't understand why, but we can't get them to change it. Or we can, really dig into the technical details and try and fill that gap between 500 megahertz to 1 gigahertz, clean up anything, any other things that maybe technology has evolved or there are better methods. So that will really depend on who joins the working group and what they want to do with it. And that leads me to kind of the last topic that I wanted to cover, which is just a pitch for people to either get involved in standards or at least consider getting involved in standards. Most of these committees, not all of them, but definitely ANSI and definitely IEEE, you don't have to pay anything to be part of a working group, and you don't even have to be a member. At least at the IEEE, you do not have to be a member of IEEE to sit on an IEEE working group that's actually going to, draft the technical content of a document. Now, in both those cases, you do need to be a paid up member in order to vote on the ultimate standard. But let's face it, I mean, if you want your voice to be part of the process, being part of that drafting committee, that's where you can express that voice. Now, again, that's not true for all standards committees. ISO and CISPR, you do have to, pay in to just to be part of those working groups. But there are informal committees that also have some insight into what's going on there. The SAE is really good about that. So if any of those things are interesting to you, if there are standards that you're aware of that sort of hit you right where you're working, and you want to have some say, you see where things could be improved or where things have evolved, look for avenues to get involved in those standards working group efforts. Contact me and I can try and get you hooked up with the right people. The other thing is that I know that I felt when I was a little bit more junior, not that I'm not still junior compared to some folks, but it seemed like the people who wrote standards must be, everybody with 50 years of experience and every lessons learned and every fact at the very tippy top of their minds on a particular topic. And certainly there are those people in standards working groups and we need those people, but it is useful to have a range of experiences on a working group, because one of the problems with once you've been around a long time, you've seen everything, it's a little hard to remember sometimes what's not obvious to a new or a naive reader. because let's face it, if you wrote standards only for experts, or that only experts could understand, the experts don't need the standard, right? It's the guy who just got, assigned to do a particular test or to solve an EMC problem. That's the guy who needs a standard to reference, and there's a lot that they don't know. The other thing is that people who are a little earlier in their careers, again, they remember what it's like not to know everything. And they're also seeing technology evolve at a different level than the folks who have been around, for multiple decades. So getting those additional perspectives involved in standards drafting working groups is really one of my major priorities as VP of Standards for the EMC Society. For anybody who's going to the symposium this year, I don't think this is published anywhere yet, but I want to let you know, because it should be publicized when the final program comes out, that we're organizing a happy hour sort of meet and greet networking event that will be free, with free drinks and appetizers for anybody who sits through an entire standards meeting. And that could be one of the working groups in a field that's of technical interest to you. It could be the Standards Development and Education Committee. It could be what we call SATCOM, so Standards Advisory Committee. For anybody who participates in one of those meetings, we will give them a ticket to, again, a sort of happy hour event on the Thursday afternoon of the symposium. So that's kind of a way to bring more people in, to say thank you to all the people who do contribute so much to the standards. For the EMC Society, we kind of live and die by standards in a way that not every discipline does. I'm sure a lot of us have had the sense that if it weren't for regulatory requirements, you could never get EMC to see the light of day when it comes to like management priorities. So the other thing to think about is that if you see a place in your technical area where there could be a standard or should be a standard and there isn't one right now, the IEEE EMC Society can help you develop a new standard. We have training for new working group chairs. We have resources that you can lean on. We've got a really good relationship with the IEEE Standards Association. So if that's something that you feel would be important, again, please get in touch and let us know, and we'll do everything that we can to help. So all that being said, that was a whole lot of me talking. If anybody has any questions or opinions or war stories about standards or answers to any of my, standards mysteries, please let me know, but I will stop talking for a minute and throw the floor open.
Okay, very good. Thank you, Karen, so much for your presentation. It was the most exciting standards presentation I've ever seen. So,
it's easy to succeed when the bar is so low.
So at this time, you can unmute yourself and ask Karen a question. There's a hand up, I see. Nitin. Nitin, go ahead, unmute. Nitin, can you unmute your mic?
Yeah, can you guys hear me?
Yeah.
Yes.
Okay, probably just a very basic question. So what are these standard limits usually based on? Like, what is the basis for setting up like a limit? For example, if I'm referring to like radiated emissions, I always see like, at certain frequencies, the limit is something, and as I go upper in the frequency, the limit is low. So what is the basis for that?
Yeah, absolutely. That's a fantastic question. And by the way, Jerry Meyerhoff, I just opened the chat, and he's got a good explanation of the difference of why 9 kilocycles or kilohertz versus 10, and then 120 versus 100. And it ties into your question, which is generally speaking, the drafters of a standard have a particularly sensitive receiver in mind. And they want to protect that class of receiver against threats in its frequency range. So, the monopole rod antenna region of CISPR 25 and RE102, it used to be that the rod antenna was the thing you needed to protect for both AM and FM broadcasting. And so having that monopole, that the monopole is the rod, 41 centimeter rod antenna test region of the radiated emission standards. That's a really tricky test to pull off in a way. It's the least repeatable when you go from lab to lab. But that monopole antenna was for a long time, absolutely typical of the kind of receiver you were trying to protect in that frequency range. And for MIL standard 461 RE102, actually a large part of what I do for various customers in the aerospace and defense realms is we take the known receive antennas on a platform, figure out sort of what their susceptibilities would be, and then tailor limits for the units that are going to go on that platform, share that platform with those particularly sensitive receivers, tailor the radiated emission limits on those units specifically to protect those receivers. So that's, now of course that gets harder the more general your standard is, right? It's really easy for me to tailor RE102 for a unit that is just going to go on one satellite that has a very well-defined set of receive antennas. If I'm the FCC and I have to protect everything in the known universe, and because you could, take a walkie-talkie and carry it anywhere, you've got a little bit of a different mindset. But that's really what people are thinking about when they're trying to set those limits.
Okay, next question. If you have a question, go ahead and unmute and ask Karen.
I have a comment.
Hey, Kimball, how's it going?
It's going.
Glad to hear from you.
The question about how do you determine the distance, or what determines the standard distance, probably one of the most classic examples of that is the FCC limits on radio emissions from automobiles. They picked what's the normal distance between a vehicle on a road and a house on the side of the road. Okay, we'll use that. We'll make that official. Okay, done.
Which really makes you wonder, like, how did they determine what was normal or average for that kind of arrangement?
Similar to the why are we going to use a 41-inch long monopole for the low frequency work for radio immunity and emissions? And that was, what's the distance between the cockpit of a aircraft and the receiver and the line that goes up to the top of the aircraft to connect to its outside antenna? Oh, 41 inches. Okay, standard.
Yeah. And, at a certain point, a lot of these things are arbitrary, just like you're pointing out, but the ones that have stood the test of time, they're good enough, right? Even though you can't, point to some of these things and say, oh, yes, with absolute analytical rigor, we have made this test setup. It's always that trade-off with EMC, right? What's feasible to test within a reasonable cost and schedule, and what's enough information to throw up warning flags if there's going to be a problem. It's I was actually I was having to introduce RE102 to an RF group at a university. And it's a fantastic RF group, and they've got great facilities. They've been wonderful partners, but they took one look at RE102 and they were aghast when I said, oh yeah, we need to do testing per this standard. And they looked at it and they were like, this is useless. Why would anybody do this? They actually told me that I should go change the standard. And I was like, I could get back to you in 10 years when somebody lets me on the Tri-Services Commission, or maybe we could just do it. And, there are reasons. But, from their point of view, RE102 is a horrible test because it's only one data point at one distance away from, the unit under test. They're used to characterizing, all different, angles for like an antenna pattern. but you know, it's good enough, right? Most of the time, if you meet your RE102 limit, CISPR 25 limit, or what have you, most of the time when you get integrated onto your platform, things are going to be okay. 100% of the time, definitely not, but most of the time it's good enough, right?
Okay, very good. Do we have another question or comment?
Oh man, I did put everyone to sleep. Darn it.
I don't know. Oh, there's a hand up. Daniel raised a hand. Go ahead, Daniel.
Excellent presentation, Karen. Question for
Thanks.
you. There seems to be a big push right now in the automobile industry to remove AM radios. And hold on. I don't think it's a political thing. I think it's actually an EMC thing. In other words, they're finding that the AM radio is much more sensitive to EMC than the standards that they would otherwise have to meet. What do you think about that? Is really the source of the objection for the AM radio?
Okay, so my impression, and then we can just open the floor because I know a lot of people in this audience have been aware of this issue. My impression is that in electric vehicles, the switching frequencies of the inverter that powers the actual EV motor have harmonics that fall very strongly in the AM band. And it becomes much more difficult, not impossible, but much more difficult to ensure that you have good AM reception across the band without picking up the noise from your own inverter system controller. And so, you know, there were some manufacturers or some engineers somewhere or something that basically said, hey, you know, people don't use AM radio so much. Why are we spending so much time and money trying to protect it? And I think you're exactly right, that it is an EMC concern that was driving the push. But then, holy moly, did that get turned into a thing. So again, I've only nibbled around the edges of it. I say, I know every vehicle that I worked on at Ford, we were able to protect, you know, get the EV system to play nice with the AM radio. So I know it can be done. But yeah, I'll just open that up to comments because I'm sure there are people here who've been much more deeply involved in that than I have. But boy, did that turn into a brouhaha.
Let me ask a tangential question regarding that too. Would the reduction of interference with AM radio also have the side benefit of improving resistance to EMP attack for those EVs? In other words, because it's I understand that the major
good for her.
Major frequency of the EMP is in most of its power is in the 4 megahertz region, and that might have beneficial improvement of resistance to an EMP pulse. What do you think about that? Or if the rest of the audience has much more informed comment, I'd be very interested to hear.
Yeah, I see Connie raised a hand. Connie, do you have a comment on it?
Yeah, in the United States, the IPAWS system, which is this huge multi-layered, multi-agency, multi-channel notification system, is predicated on AM radio because of its range and availability, not FM radio. And so the government has kind of said, if you don't have AM capabilities, the person in your vehicle will not get an emergency, is more likely not to get an emergency notification because the notification isn't going out through the FM bands, it's going out through the AM bands. And so there's quite a bit of controversy on that now, because I know that the European car manufacturers, I believe Mercedes and BMW no longer support AM radio. But in this country, the feds have said, you know, you can't put people in peril just because it takes a little more doing to shield from it's the charging system in the electric vehicle that gets into the radio and messes it up. So that's still an ongoing discussion.
Yeah,
thanks.
In your backyard where you are right now, KMOX St. Louis is a 50,000 watt AM station there, and they are one of several AM stations throughout the country that has an entire diesel generator, transmitters, miniature studio, all inside of steel enclosures right now that after the EMP goes off, those things will get used and fired up, and that's how they'll get back on the air. And there's a number of those throughout the country. And there's a nice YouTube video all about it if you're ever interested about KMOX.
Right, and I know that there's a 50 kilowatt transmitter close to Denver that's in exactly that same situation. The guys who ran the Lockheed Martin EMC chamber down in South Denver affectionately referred to it as the blowtorch of the West, because of the way that the energy from that particular transmitter could just go right through the shield their chamber walls. So yeah, but that did give me a chance to think through. I don't think that quieting down the most noisy system, which is the inverter, would necessarily help the vehicle's overall EMP responsiveness, mostly because the EV system itself, the high voltage system, is almost, I mean, obviously not completely, but it's largely immune to radiated and conducted noise effects or immunity susceptibility. The controllers are the ones that would be vulnerable, and they wouldn't change based on this issue. So that's my thinking about it, but that's, you know, based on, you know, 45 seconds of musing or so, not rigorous analysis.
Okay, very good. Any more questions or comments? Okay, not hearing any, I'd like to move on to our drawing. We did have 92 people pre-registered for this meeting. I was looking at the wrong information. We had 92 pre-registered for the meeting. We had 47 people online. Some of them did not pre-register. At least I couldn't find them when I went through the records. So if you're one of the pre-registered people, then you are eligible for the drawing. I use a random sequence generator from random.org. So we're going to go through, starting at the first number that was drawn here. For the first one will be for a $25. So you must be present to win. The first random number is 24. 24 is Gopinath Gampala. Are you online? I did not see you. Okay. The second number was number 92. Mark Zeidman. Mark, I showed you were present. Mark, are you still here?
Yep.
If so,
I
unmute.
am still here.
Very good. So, Mark, congratulations. You won a $25 gift card from Amazon, and I'll be emailing it to the email you used for this reading at your for this meeting at your Gmail. Congratulations.
Thank you very much.
The next one is for $25, and that is number 21. 21 is David Evans. David, are you still here?
Yes, I'm here. Thank you.
Very good. Same for you. Congratulations. And David at evans.org. You'll be getting the email from Amazon, not from me. So watch your junk mail folders, guys and gals. Third number is for the $75. And that is number 78. 78, Philip Sturkich. Philip,
That's
are you
me.
still here?
Yes, sir. Here I am.
Oh, congratulations, Philip.
Thank you.
Boy, this is one of the quickest ones we've ever done. Usually this goes on and on for a period of time, but not today.
Let me make
So
sure.
anyway, that worked out.
Let me make sure. What did I win?
You won a $75 gift I call it a card, but it's you know, you get an email from Amazon and it on anything you like on Amazon.com.
Excellent. Thank you. Thank you. You're generous people.
Oh, no problem. That's all that I have. Does anybody else have anything else before we can stay online if people want to chat, or I'm going to stop the recording at this time.